All right, let's dive right into this explainer and uncover the invisible rules that govern literally how we see the world around us. I mean, have you ever stopped to wonder why you can't see a single thing in a pitch-black room, but the absolute second a light flicks on, boom, everything is instantly visible? It's all about how light interacts with matter, bouncing off surfaces and carrying that visual data straight into our eyes. And today, we're going to unpack exactly how that whole process works.
Let's start with a bit of everyday magic. Have you ever looked at your reflection in a shiny spoon? Notice how your image actually flips upside down depending on which side you're looking at? Or, if you pull the spoon away, your face completely changes size and shape. You've probably messed around with this at the breakfast table, but what you're actually doing is playing with some of the absolute most fundamental laws of optics.
So here's our roadmap for today's explainer. We're going to cover the magic of light, meet the spherical mirrors, map out images with rays, explore real-world mirrors, tackle the math behind it all, and finally, finish up with the illusion of refraction. Let's get to it. Section 1. The magic of light. Straight lines and shadows. The absolute crucial takeaway here is that light pretty much always travels in straight paths. And that perfectly explains why solid objects cast such sharp, precise shadows. Moving right along to Section 2, spherical mirrors, concave versus convex. Let's return to our spoon analogy for a second to see exactly how curved surfaces completely change the rules of the game. This is such a brilliant way to illustrate the difference. So, a concave mirror curves inward, facing the center of an imaginary sphere. You can kind of think of it like a cave that you can walk right into. Just like the bowl of your soup spoon. A convex mirror, on the other hand, bulges outward toward the light source, exactly like the backside of that very same spoon. Now, to really understand how these mirrors manipulate light, we got to map out their anatomy. And let's start right on the surface of the mirror itself. The exact geometric center of that reflecting surface is a point we call the pole. We just represent that with the letter P. You can think of this as our starting line, the anchor point from where we'll measure, well, pretty much everything else. Next up is the center of curvature, which we mark as C. Remember that imaginary glass sphere we just talked about? Well, C is the absolute center of that sphere. And notice that it sits completely outside the actual reflecting surface. For a concave mirror, it's hanging out right in front. But for a convex mirror, it's hiding completely behind the mirror. Okay, the principal focus, or F. This is where the true magic happens. If you were to point a concave mirror directly at the sun, this is the exact spot where all that sunlight converges into a single, intensely hot point, a point that can literally burn a piece of paper. And the distance from our pole to this principal focus, that gives us our focal length. Now, check out these two mirrors in action side by side. It's super cool. The concave mirror on the left grabs all those parallel rays of light and converges them tightly into a single, sharp point right at the focus. But then look at the convex mirror on the right. It acts almost like a scatter gun, pushing those parallel rays apart so they diverge. It actually makes it look as if the light is radiating outward from a focus hiding behind the mirror. That brings us to Section 3, mapping images with rays, basically predicting the future. Let's see how we can actually map these reflections out without needing a supercomputer. Ray diagrams are just this beautifully simple geometric tool. They let us predict exactly where a reflection will appear, how big it's going to be, and whether it'll be upside down. And the best part? You only need to draw two simple lines using some consistent rules. First, any ray coming in parallel to the main axis is always going to reflect straight through the focus. Always. Second, any ray traveling through the center of curvature hits the mirror dead on and bounces right back along that exact same path. Wherever these two reflected lines cross paths, boom, that is exactly where your image appears. It's like solving a giant puzzle, but super easy.
All right, this is your ultimate cheat sheet for concave mirrors right here. And I want you to notice the pattern. As you move an object from really far away, closer and closer to the mirror, the image starts off tiny, real, and upside down. But once you cross that focal point and get super close to the glass, the image suddenly flips. It becomes virtual, right side up, and highly magnified.
On to Section 4. Mirrors in the real world, the superpowers of reflection. So, why does all this geometry matter to you? Because these exact properties are engineered into the tools we use every single day. Think of concave mirrors as our primary tools for focus and magnification. When you need a super powerful, straight beam of light piercing through the pitch dark, you put a bulb right at the focus of a concave mirror. That's exactly how your car's headlights work. Dentists use them to get a nice magnified view of your teeth, and those massive solar furnaces use them to catch sunlight and concentrate it into incredibly intense heat.
On the flip side, convex mirrors are basically your driving superpower. Have you ever noticed that the passenger side mirror in your car says, "Objects in mirror are closer than they appear"? Yeah, that's a convex mirror. Because it bulges outward, it takes this massive area of the road behind you and shrinks it down into an upright, wide-angle view. It's literally what keeps you safe in traffic.
Let's transition to Section 5, the math of mirrors, the matrix of light. Time to peek at the underlying code that makes all this work. Okay, please do not let the phrase new Cartesian sign convention intimidate you. Seriously, it works exactly like a basic middle school XY graph. The pole of the mirror is simply 0, 0. If you measure distance to the left towards your object, it's a negative number. If you measure to the right, behind the mirror, it's positive. Above the line is a positive height, below the line is negative. It really is as simple as that.
And behold, the mirror formula. This wonderfully elegant equation is the master key for all spherical mirrors. So U is your object distance, V is your image distance, and F is your focal length. If you know just two of these numbers, you can instantly calculate the third. It mathematically proves every single thing we just saw in those visual ray diagrams.
Then we have this magnification formula, which tells us the scale. Basically, it tells us how much the mirror is stretching or shrinking the reflection. Oh, and here's a fantastic little shortcut for you. If your final magnification number has a negative sign, it quickly reveals that your image is real and inverted, meaning it's literally hanging upside down in space. Finally, we arrive at Section 6, the illusion of refraction, or bending light. So, what actually happens when light doesn't hit a solid wall, but enters a totally new, transparent world? Just think about some of these real-world optical illusions for a second. When you look into a clear pool, the bottom definitely seems shallower than it really is, right? Or if you drop a pencil into a glass of water, it looks completely snapped or bent at the waterline. These aren't just tricks your brain is playing on you. They are actual physical phenomena occurring right at the boundary between air, water, and glass. So, the absolutely crucial point here is that light doesn't always travel at the exact same speed. As a light ray leaves the thin air and plunges into a denser medium, like water or thick glass, it hits the brakes. It actually slows down. And entering that new medium at an angle while changing speed causes the path of the ray to physically bend. And that, my friends, is refraction. We've completely unlocked the secrets of the mirror and how light reflects to show us the world around us. But this fascinating, completely mind-bending reality of refraction, how lenses work, how a glass prism creates a literal rainbow, and how our very own eyes actually process images, well, that is exactly what we're going to explore next time. So, the question I'll leave you with is this. Are you ready to see just how deep the rabbit hole of optics really goes?